The languages you see used the most for machine learning tasks are Python, Julia, MATLAB, and R. All of these languages are considered high-level languages and are meant to be readable and easy to write for their target communities. Python is a relatively mature language first developed in the early 90s. It is a high-level, multi-purpose language that is also used in many applications outside of machine learning. It is open source and free to use. You can accomplish some basic tasks with the base language, but you can get the most out of Python through its diverse package ecosystem. Many of the standard packages used in the machine learning community are Python packages. Julia is a relatively new language developed with the aim to be both high-level and high-performance. While many high-level applications act as a wrapper around a low-level language like C to perform heavier computational tasks, Julia is performant enough that much of the language and packages are written in Julia all the way down. Because of this, the average Julia programmer can read the Julia language and package source code fairly easily. Julia has a strong focus on scientific and numerical computing and is also open source and free to use. Julia has its own growing package ecosystem, but also provides the ability to call functions from other languages, allowing you to make use of packages written in Python and other languages as well. R is a language developed by statisticians specifically for statistical computing and graphics. For that reason, it is often used in domains that use programming mainly for statistical tasks, such as life sciences, economics, and social sciences. Like Python and Julia, R is an open source language that anyone can use for free. Since it is developed for statistics, R provides a lot of statistical functionality out of the box, but also has a rich library ecosystem for more specific tasks, including machine learning. MATLAB is a high-level numerical language that is very popular in fields with heavy usage of math, such as engineering. MATLAB stands for Matrix Laboratory, as the main data type for the language is a matrix. Most mathematical functionality is provided in the base language, and a series of toolboxes provide more domain-specific functionality. MATLAB is a licensed product, and many of its toolboxes require additional licenses. Although a free, open-source version, Octave, is also available. Most of the syntax is the same, but Octave does not have all of the toolboxes that MATLAB provides. Much of MATLAB's machine learning functionality is provided in toolboxes, such as the statistics and machine learning and computer vision toolboxes. Assuming you have chosen a language, what tools are available in that language? Here we are showing the common data types and packages that are used for machine learning tasks. In general, each language has some sort of plain array data structure that can store different types of elements, and some sort of structured array or table that is more human readable, which often are referred to as data frames. Arrays can come in a number of different dimensions and are the most basic storage object. In Python, most machine learning applications use NumPy arrays, which are available through the NumPy package. In the other three languages, some sort of array or matrix data structure is available through the base language. Data frames, or tables in MATLAB, are provided for the convenience of the analyst. They provide named columns, rows, and often some ability to print out summary statistics. Data frames are pretty nice for working with tabular data, but if you are working with something like images, an array or a matrix is the way to go. Data frames are great for interactive data analysis, but when it comes to larger data and more time-consuming tasks, arrays are a simple data structure that scale much more nicely. I've also listed a couple of packages that are used in machine learning today for each language. Because machine learning and AI is a quickly changing field, the most popular packages may evolve and change in the future. We'll go through some of these more in depth in another video. In Python, Julia, and R, you explicitly load the package you are interested in, whereas in MATLAB you can use the functionality from a toolbox without explicitly loading the toolbox. Next, I'm going to show you a simple example in each language fitting a linear regression to a set of data. Keep in mind that the example is a statistical one, The purpose of the demo is mainly to give you an idea of the look and feel of each language. The first step is to read in your data. In this case, I have a TSV data file, which I am specifying with the file name variable. This is a dataset from NASA that I found on the University of California, Irvine Machine Learning Repository. On a high level, this dataset contains the noise measured by different designs for airfoils, or wing shapes for aircrafts. In each, we are reading the data in as an array and as a data frame. Because the file doesn't contain headers, I'm specifying them when I create the data frame. In R, where I specify the column names, the C stands for concatenate and is how you would create a vector from scratch. In this case, the vector of column names. In Python, I'm using the pandas package for the data frame and NumPy for arrays. In Julia, I'm using the delimited files package, which comes with the base language, to read the data into an array, the readdlm function, and the data frames and CSV packages to read in the data and use data frames. Here is the output showing what the first 5 rows of each array and data frame look like in each language. Notice that in R they look the same. R matrices have columns just like data frames. However, there are some slight internal differences to matrices and data frames in R, and some functions are only designed to take one or the other. Most data frames have some sort of summary function that give you information about the columns. Sometimes it's called describe. Most have the minimum, maximum, median, and mean values. R and Python also list quartiles. A common pre-processing step is to rescale the values of each feature to be in a similar range. Some machine learning models will favor features with high values. Here we write a simple min-max normalization function. In all of these cases, we would like to run this function on both the data frame and array versions of our data. In R, values in a data frame and array can be accessed and rewritten with the same syntax. But in Python, Julia, and MATLAB, this is done slightly differently between the two types. In Python and MATLAB, we handle this with an if statement checking the data type within the function. In Julia, we can specify the data type of the input and overload the function for different data types. The main function takes in an array, and an additional function converts a data frame into an array and back to a data frame again once the normalization is done. An additional thing to note for MATLAB is that MATLAB functions must be each saved in their own file, with the file name matching the function name. After we rescale our values, we can call the summary or describe function again, and see now that all our values are between 0 and 1. Next, we'll fit a linear regression to our data. We're going to fit 2 models, one predicting sound level from just frequency, and the other using all 5 columns to predict sound level. In R and MATLAB, we don't need to load any particular package, although the FitLM in MATLAB does come from the statistics and machine learning toolbox. In Python, we use sklearn, and in Julia, we use GLM, which stands for Generalized Linear Models. sklearn is very particular and requires array inputs of a particular shape. Julia, R, and MATLAB allow a special syntax to describe the model where you can write out the names of the features you are interested in. In MATLAB, if you just give the FitLM function a table, it will assume the last column is the one you are trying to predict, and all others are features. Julia and MATLAB give a lot of information when you print out the model that can be helpful for regression analysis. The summary function in R will give you similar information, and Python's sklearn package provides functions to get this additional information as well. Next, we'll evaluate our models. I'm writing a function that prints out the mean absolute error, the mean squared error, and the R-squared values for an input model so we can compare them. Again, the MATLAB function must be in a separate file. In Python, sklearn has a subpackage, metrics, that will calculate these for us. The others have similar functions or properties stored within the model that contain this information as well. In Julia, we load the statistics package, which comes with the base language to calculate some of these. You can also see a bit of how to format string output in each language. Here are our metrics for each model. As we would want, the quality of the models are the same across languages. Within each language, Model 2 has lower errors than Model 1, and in particular, the R-squared value jumps from roughly 0.15 to 0.52. If I were to continue this exercise, I might go back and start removing features to see how much the R-squared changes to get an idea which is contributing the most to the model. To get an idea of the look and feel of creating plots in each language, we're going to plot a histogram of the residuals for our model. The residuals are the individual errors for each data point. Here I'm making 3 subplots in the same figure, 2 for the residuals of each Model 1 and Model 2, and a third showing both histograms in the same plot. It's important to note that in Python, Julia, and R, this is demonstrating one way to do the plotting. There are other packages available that may look and behave differently. In particular, I'm showing R's native plotting capability, but ggplot is also very popular. Julia has a nice meta package, Plots, which allows a common interface to many plotting backends, including pyplot, which we show in Python. The statsplots package contains additional functions for statistical plots. MATLAB's statistics toolbox has a specific plot residuals function that we can make use of. Here are the resulting plots from the code we ran. The shapes are roughly the same across languages, but the bin sizes are a bit different. They all have the ability to show legends and edit titles and access labels. If you have the full MATLAB interface, you have the ability to interactively change plot attributes and produce the code that would do those changes programmatically, which is a nice feature if you have to make a lot of plots. That concludes our discussion on different programming languages used in machine learning. As I mentioned earlier, the goal was to give an overview of some of what is available. I hope you have gotten a feel for some of the languages that are used the most in machine learning and what each has to offer.